There's something hauntingly beautiful about the unknown, the way it lingers at the edges of our understanding, whispering secrets we can't quite grasp. Picture this: you're floating in the infinite blackness of space, surrounded by stars that have burned for billions of years, and suddenly you encounter something that shouldn't be there. A signal with no source, a void where matter simply vanishes, a flicker of light that defies every law of physics we've ever written. These aren't scenes from science fiction. They're real, documented mysteries of the intergalactic medium, phenomena so puzzling that even the most brilliant astrophysicists can only stare at their data and wonder. Today, we're embarking on a journey through 34 of these cosmic enigmas, each one a testament to how little we truly know about the universe we call home. Think about the last time you looked up at the night sky and felt small under its expanse. That feeling, the awe, the curiosity, is exactly what drives scientists to unravel these mysteries. Take the strange radio signals known as fast radio bursts, for example. These blips of energy travel across billions of light years, lasting just milliseconds, yet they pack more power than our sun emits in decades. No one knows what creates them. Or consider the Great Attractor, a gravitational anomaly so massive it's pulling entire galaxies toward it, including our own Milky Way. We can't see it, we don't know what it is, but it's there, lurking in the cosmic shadows, reshaping our corner of the universe. These aren't just scientific curiosities, they're clues to a reality far stranger than we've ever imagined. What makes these mysteries so thrilling isn't just their strangeness, it's what they reveal about our place in the cosmos. Every unexplained signal, every ghostly void, is a reminder that the universe is still writing its own rules, and we're just beginning to read them. Some of these puzzles might hold the key to understanding dark matter, the invisible glue holding galaxies together. Others could rewrite Einstein's theories or even hint at civilizations far beyond our own. The truth is, we're standing on the edge of discovery, peering into the unknown with tools that grow sharper every day. So, if you've ever wondered what lies beyond the limits of human knowledge, you're in the right place. By the end of this journey, you'll see the cosmos not as a static backdrop of stars, but as a living, breathing mystery, one that's waiting for us to unravel it, one enigma at a time. Imagine the universe as a vast, invisible river, one that flows in a direction we can't quite explain, carrying entire galaxies along its current. That's the essence of the dark flow, one of the most baffling phenomena in modern cosmology. It started with a simple observation. Galaxy clusters, those colossal families of stars and dark matter, weren't just drifting apart as the universe expanded. Instead, they were all moving together as if pulled by some unseen hand. Not just a few of them either, hundreds, maybe thousands, all streaming toward the same patch of space at speeds topping 2 million miles per hour. At first, scientists thought it was a fluke, an error in the data. But the more they looked, the clearer it became. Something out there was tugging on the cosmic fabric, and it wasn't playing by the rules. The strangest part, this gravitational pull doesn't seem to come from anything inside our observable universe. No supercluster, no black hole, no concentration of dark matter we've ever detected could explain it. That's led to some mind-bending theories. One possibility is that the dark flow is evidence of a neighboring universe, another bubble of space-time just beyond the edge of our own, exerting its gravity on us like a cosmic neighbor leaning over the fence. If true, it would mean our universe isn't alone, but part of a vast multiverse we've only begun to glimpse. Another idea is that the flow traces back to the very birth of the cosmos, a relic of the uneven forces at play during the Big Bang itself, like ripples frozen in time. Yet every explanation raises new questions. If another universe is pulling on ours, why can't we see any trace of it? If it's a remnant of the early universe, why hasn't the expansion of space smoothed it out over billions of years? Even the most advanced telescopes and simulations struggle to make sense of it. The dark flow doesn't just challenge our understanding of gravity or cosmic structure. It hints that there's a whole layer of reality we haven't even begun to map. And that's what makes it so exhilarating. This isn't just a puzzle for astrophysicists. It's a reminder that the universe still holds surprises big enough to rewrite the textbooks. The next time you gaze up at the night sky, remember, out there, beyond the stars, something immense and invisible is pulling us into the unknown. Hidden behind the curtain of our own Milky Way, where starlight dims into cosmic dust, lies a gravitational enigma so powerful it's bending the motion of galaxies like a puppeteer pulling strings. This is the Great Attractor, a mystery that's been tugging at the fabric of our local universe for decades, yet remains stubbornly out of sight. Picture hundreds of galaxies, including our own, all streaming toward the same invisible point in space at over 1 million miles per hour. It's as if the cosmos itself is whispering, "Follow me." But when we turn our telescopes toward the source, we're met with a cosmic blind spot, obscured by the very stars and dust of our galactic backyard. What makes this anomaly so perplexing isn't just its strength, it's the way it defies expectations. Early theories pointed to a supercluster of galaxies, a dense knot of matter with enough gravity to explain the pull. But when astronomers peered through the interference using infrared and radio telescopes, what they found was both underwhelming and unsettling. The mass they could see, the galaxies, the gas, the dust, wasn't nearly enough to account for the tremendous force at work. That left only one conclusion: something invisible, something we still don't fully understand, is doing the heavy lifting. Enter dark matter, the universe's most elusive architect. Could the Great Attractor be a fortress of this mysterious substance, a concentration so vast it warps space-time on a scale we've never seen? Or is it something even stranger? The plot thickens when you consider the attractor's location. It sits in what astronomers call the zone of avoidance, a region of the sky where the Milky Way's dense disk blocks our view. It's like trying to study a distant city through a fogged-up window, but recent breakthroughs, like the discovery of the Vela supercluster lurking behind the veil, suggest we're only scratching the surface. Some scientists now believe the Great Attractor might not be a single object at all, but the tip of an iceberg, a sprawling network of dark matter and galaxies stretching far beyond our current maps. Others speculate it could be a gravitational echo from the early universe, a relic of the primordial fluctuations that seeded all cosmic structure. What's truly humbling about this mystery is what it says about our place in the cosmos. Even in our own galactic neighborhood, just a few 100 million light-years away, we're still piecing together the puzzle. The Great Attractor isn't just pulling galaxies, it's pulling our understanding of the universe into uncharted territory. Every new observation, every clever workaround to peer through the dust, brings us closer to answers that might rewrite the rules. So the next time you hear about dark matter or cosmic flows, remember, there's a hidden force out there bending the paths of galaxies, and it's waiting for us to uncover its secrets. One moment, it's silence; the next, an explosion of radio waves brighter than 1 billion suns, all crammed into a fraction of a second. Fast radio bursts are the universe's most enigmatic flashes, cosmic Morse code blaring from the depths of space with no obvious sender. First discovered in 2007, these bursts pack more energy in their fleeting existence than our sun emits in 80 years, yet they last less time than it takes to blink. And then, just like that, they're gone, leaving behind a trail of static and scientists scrambling for answers. What makes these signals so baffling isn't just their power, it's their unpredictability. Some burst once and never return, like a firework lighting up the cosmos before vanishing forever. Others repeat, flashing on and off in patterns so erratic they defy prediction. Take FRB 1211, for example, a repeater that cycles through periods of frantic activity followed by eerie silence, as if something, or someone, is switching it on and off. Then there's FRB 1809, a burst so close and loud it was detected by a telescope originally designed to study the Moon's surface, not deep space anomalies. Each discovery peels back another layer of the mystery, revealing just how little we know. Theories about their origins range from the plausible to the downright fantastical. On the natural side, magnetars neutron stars with magnetic fields trillions of times stronger than Earth's are prime suspects. When these cosmic powerhouses quake or flare, they might unleash bursts powerful enough to reach across galaxies. But not all FRBs fit this mold. Some arrive with a polarization twist, their radio waves corkscrewing through space in ways that suggest they've traveled through incredibly dense magnetic fields, far beyond anything a magnetar should produce. That's led some researchers to propose even wilder explanations, like cosmic strings, hypothetical defects in spacetime left over from the Big Bang, or even colliding black holes. And then there's the elephant in the room. Could these bursts be artificial? It's a question that lingers, not because of evidence, but because we can't yet rule it out. The idea isn't as far-fetched as it sounds. If humanity ever built an interstellar beacon, it might look a lot like an FRB brief, bright, and engineered to cut through the noise of the universe. Of course, extraordinary claims require extraordinary proof, and so far, every FRB has a natural explanation that's more likely. But the mere possibility keeps the debate alive, a reminder that in a universe this vast, we'd be arrogant to assume we're the only ones listening or signaling. What's truly remarkable is how these tiny flashes are rewriting astronomy. FRBs act like cosmic lighthouses, their signals distorted by the gas and plasma they pass through, allowing scientists to map the invisible matter between galaxies. They're also time machines of sorts. Every burst carries a timestamp. The longer it takes for higher frequencies to arrive, the farther it's traveled. This dispersion measure lets astronomers calculate distances across billions of light years, turning FRBs into tools for measuring the universe itself. Yet for every answer, a dozen new questions emerge. Why do some repeat while others don't? What creates their mind-bending energy? And why do a handful seem to originate from galaxies with extreme environments, like those teeming with star formation or harboring supermassive black holes? Each burst is a breadcrumb on a trail leading deeper into the unknown. One thing's certain, fast radio bursts aren't just cosmic oddities. They're proof that the universe still has cards it hasn't shown us. And as our telescopes grow sharper, we might finally be on the verge of reading them. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, so many worlds that the math suggests life should be everywhere. And yet, when we listen, when we search, all we hear is silence. This eerie contradiction is the heart of the Fermi Paradox, a puzzle so profound it forces us to question everything we think we know about life, intelligence, and our place in the cosmos. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" the paradox cuts to the core of one of humanity's oldest wonderings: are we alone? On paper, the numbers are overwhelming. Take just our own Milky Way, with over 100 billion stars, many hosting planets in the habitable zone. Even conservative estimates suggest thousands of civilizations could exist right now in our galactic neighborhood. By now, some should have spread across the stars, built megastructures, or left traces even our primitive telescopes could spot. But the sky remains stubbornly quiet. No signals, no artifacts, no visitors. It's as if the universe is a stage set for a play where we're the only actors. And that's what makes the paradox so haunting. Scientists have proposed dozens of explanations, each more chilling than the last. The simplest is that intelligent life self-destructs before it can reach the stars. Whether through war, environmental collapse, or runaway technology, perhaps every civilization hits a filter, a wall of existential risk that none survive. If true, the Great Silence isn't just a mystery, it's a warning. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interfere, observing us like animals in a cosmic nature preserve. It's a comforting thought until you realize it implies we're the ones in the cage. Other theories stretch the imagination even further. Maybe we're looking for the wrong signs. Advanced life might not use radio waves, but something we can't yet detect, like neutrino communication or quantum entanglement. Or perhaps intelligence is so rare that Earth is the first spark in a universe still waking up. Some argue that spacefaring civilizations inevitably turn inward, creating virtual realities so compelling they lose interest in the physical universe. And then there's the darkest possibility, that we're truly alone, a 1 in a trillion fluke in an otherwise sterile cosmos. What makes the Fermi Paradox so compelling isn't just the lack of answers, it's how the question reframes our existence. Every time we point a telescope at an exoplanet or scan the heavens for signals, we're not just searching for aliens, we're searching for our own future. If civilizations routinely survive their technological adolescence, the silence suggests a destiny far stranger than we've dared to dream. But if they don't, the void might be holding up a mirror, forcing us to confront whether humanity will be the next name on the universe's long list of ghost stories. Either way, one thing's certain: in a cosmos this vast, silence is the most unsettling sound of all. It began as just another night at the Big Ear radio telescope in Ohio. Routine scans of the cosmos, the hum of machinery, the slow crawl of data across printouts. Then at 10:16 p.m. on August 15, 1977, the universe spoke, or at least something did. For 72 electrifying seconds, a signal blared from the constellation Sagittarius, so intense it maxed out the telescope's equipment. When astronomer Jerry Amon reviewed the data days later, he circled the alphanumeric sequence in red pen and scrawled a single, awestruck word beside it: "Wow." The name stuck, but the explanation never came. Decades later, the wow signal remains the most tantalizing and frustrating mystery in the search for extraterrestrial intelligence. What made this signal special wasn't just its strength. It hit all the markers scientists expected from an intentional broadcast. The frequency, 1420 MHz, a quiet band where cosmic noise is minimal, perfect for cutting through the static of the universe. The shape, a narrowband spike, the kind you'd get from a focused transmitter, not a natural astrophysical event. And the duration, 72 seconds, exactly how long the telescope's fixed gaze would capture a signal passing through its field of view. It was as if someone had aimed a cosmic flashlight directly at Earth, flicked it on, then vanished without a trace. The search for answers has been relentless. Teams have scanned Sagittarius thousands of times, hunting for a repeat that never comes. They've ruled out earthly interference. No passing satellites, no military experiments, no pranksters with radio gear. Natural explanations like comets or pulsars fall short. Nothing in known astrophysics matches the signal's unique fingerprint. Even the most skeptical researchers admit If this wasn't aliens, it was something equally extraordinary. Yet without a second pulse, the wow signal exists in scientific limbo, too perfect to dismiss, too fleeting to confirm. Theories abound, each more speculative than the last. Some suggest it was a one-time event, a dying alien beacon perhaps, or a malfunctioning probe from a long-dead civilization. Others propose it's part of a pattern we're too impatient to catch, like a lighthouse beam that sweeps past Earth only once every few centuries. Then there's the unsettling possibility that it was a deliberate test, a brief ping to see if we'd notice, a cosmic version of knocking on a door before retreating into the shadows. What lingers isn't just the mystery, it's the timing. 1977 was the same year humanity launched the Voyager probes, our first deliberate attempts to shout into the cosmic void. For a brief moment, the wow signal made it feel like someone might have been shouting back. Yet as the years stretch on without another whisper, the signal becomes something else, a reminder of how vast the universe truly is and how achingly rare contact might be. It's a single footprint on an endless beach, proof that something walked here, even if we'll never know what. Somewhere in the northern sky, hidden among the stars of the constellation Boötes, lies a cosmic anomaly so vast it redefines the word empty. Picture a sphere of darkness stretching 330 million light-years across, a region so large you could fit 10,000 Milky Ways inside it with room to spare. Now imagine that sphere containing almost nothing, no galaxies, no stars, just a chilling, near-perfect vacuum. This is the Boötes Void, a pocket of nothingness so extreme astronomers call it the Great Nothing. And its very existence shakes our understanding of how the universe builds itself. Cosmic voids aren't unusual. Space is full of bubbles where matter is thinly spread. But the Boötes Void isn't just sparse, it's a staggering desert. While typical voids might contain a few dozen galaxies, this one holds only 60 or so in its unimaginable volume, making it one of the emptiest places we've ever discovered. To put that in perspective, a chunk of space that size should host around 2,000 galaxies based on standard models. The odds of such a void forming naturally. About 1 in a million. It's like rolling a cosmic die and getting the same impossible number over and over. So what carved this hole in the universe? One theory points to smaller voids merging over billions of years, like soap bubbles combining into one gigantic emptiness. But even that doesn't fully explain the scale. Another idea suggests the void is a relic of the early universe, a frozen ripple from the Big Bang where matter never condensed. Then there's the wild card. Could something have cleared the void intentionally? While there's zero evidence for extraterrestrial engineering, the sheer extremity of the void forces us to confront how little we know about the rules or the players shaping cosmic structure. The most haunting possibility is that the Boötes Void isn't empty at all, but filled with something we can't see. Dark energy, the mysterious force accelerating the universe's expansion, might concentrate here, pushing matter away like an invisible hand. Or perhaps it's a nest of primordial black holes, remnants of the universe's birth, lurking unseen. Every time we point a telescope at the void, hoping for answers, its darkness seems to stare back, reminding us that emptiness can be just as puzzling as light. What makes the Great Nothing so profound isn't just its mystery, it's what it reveals about our cosmic maps. For decades, astronomers assumed matter was spread evenly across the universe at large scales. The void proves otherwise. It's a crack in that assumption, a silent challenge to our models. And if one such void exists, could there be others, even larger, hiding in the depths of space? The unsettling truth is that we might only recognize these gaps when we stumble into them, like explorers realizing the cave they're in is far bigger than their lantern's glow can reach. Standing at the edge of this abyss, it's hard not to feel a chill. The Boötes Void isn't just a scientific curiosity, it's a mirror held up to our ignorance. In a universe teeming with galaxies, stars, and planets, this staggering emptiness whispers a humbling truth. Sometimes what's missing speaks louder than what's there. And until we understand why, the great nothing will keep pulling us deeper into its silent, spinning void of questions. Out of all the stars in our galaxy, few have captured the imagination and confusion of astronomers quite like KBC 8462852, better known as Tabby's star. Named after the scientist who first studied its bizarre behavior, Baryon, this unassuming flicker of light in the constellation Cygnus behaves like nothing else we've ever seen. Imagine a star that doesn't just dim slightly when planets pass in front of it, but plunges into erratic, unpredictable dips, sometimes losing up to 22% of its brightness in a matter of days. That's not just unusual, it's downright impossible under our current understanding of how stars work. At first, researchers thought it might be a swarm of comets, a colossal dust cloud, or even remnants of a shattered planet blocking the light. But none of these explanations quite fit. Comets couldn't produce such extreme, irregular dimming. Dust would scatter light in ways we don't observe. And the sheer scale of the dips rules out most natural debris fields. That's when an even wilder idea emerged. What if we're seeing the shadows of alien megastructures? Specifically, a Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization to harness their star's power. The concept, first proposed by physicist Freeman Dyson, suggests a civilization might eventually construct vast orbiting panels or rings to capture stellar energy. And Tabby's star's unpredictable dimming patterns, they could, in theory, match the chaotic silhouettes of such a massive, incomplete construction project. Of course, extraordinary claims require extraordinary evidence, and most astronomers lean toward natural, if still unknown, explanations. Some propose intricate dust rings with bizarre compositions, or perhaps a young star still clearing the debris of its formation. Others wonder if the star itself is behaving strangely, with internal dynamics we don't yet understand. But the megastructure hypothesis lingers in the background, not because it's likely, but because we haven't ruled it out entirely. And that's what makes Tabby's star so thrilling. It's a cosmic Rorschach test, revealing as much about our curiosity as it does about the star itself. What's truly fascinating is how this mystery has unfolded in real time, fueled by both professional research and public fascination. When Baryon and her team first published their findings, citizen scientists from the Planet Hunters project helped analyze the data. When the star's behavior demanded more observations, a Kickstarter campaign raised over $100,000 to keep telescopes trained on it. This isn't just science, it's a collective human effort to solve a puzzle that defies expectations. Every new observation deepens the intrigue. In 2017, the star dimmed again, and astronomers worldwide scrambled to capture the event in every wavelength possible. The data revealed that whatever blocks the light isn't solid, it's patchy, like fine dust, but arranged in ways that still don't match known models. Even now, years after its discovery, Tabby's star refuses to fit neatly into any box. It challenges us to question what we think we know about stars, about alien life, and about the limits of our own imagination. In the end, whether the answer is cosmic dust or something far stranger, Tabby's star has already done something remarkable. It's reminded us that the universe is still full of surprises. And sometimes the most tantalizing mysteries aren't just about finding answers, they're about learning how to ask better questions. In the vast, silent expanse of our solar system, two tiny spacecraft began drifting off course, not by much, just enough to make scientists double-check their calculations. The Pioneer probes, launched in the 1970s to study the outer planets, were supposed to follow precise trajectories, their speeds governed by the unshakable laws of gravity. But by the 1980s, something strange became undeniable. Both spacecraft were slowing down more than they should have been, as if some unseen hand was gently tugging them backward. This tiny discrepancy, just 300 billionths of a meter per second squared, became one of the most debated mysteries in modern physics, the Pioneer Anomaly. At first, the deviation seemed almost insignificant, but in the precise world of orbital mechanics, even the tiniest unaccounted-for force can hint at something profound. For decades, researchers scrambled to explain it. Was it drag from interstellar dust? A flaw in how we model the probe's tiny thruster bursts, or something far more exotic, a crack in Newton's laws, a whisper of dark matter, or even evidence of hidden dimensions tugging at the edges of our reality? The possibilities sent ripples through the scientific community, with some suggesting this could be the first hint of physics beyond Einstein's relativity. Then, in 2012, painstaking analysis seemed to crack the case, the culprit heat, not from some cosmic source but from the probes themselves. Pioneer's nuclear power sources emitted warmth, and as that thermal radiation bounced off the spacecraft's asymmetrical surfaces, it created a tiny but constant push like sunlight gently pressing on a solar sail. When researchers modeled this effect, the numbers finally aligned, case closed, or so it seemed. Yet for some, the anomaly never fully lost its intrigue. The thermal explanation, while elegant, required assumptions about how heat radiated from every bolt and panel, variables that couldn't be perfectly measured retroactively. A handful of scientists still wonder, could there be residual unaccounted-for deceleration, a shadow of something deeper? After all, the universe has a habit of using small anomalies to point toward monumental discoveries. Neptune was found because Uranus's orbit didn't quite match predictions. Mercury's wobble hinted at general relativity. Might Pioneer's drift still hold secrets we haven't unraveled? What makes this mystery so compelling isn't just the science, it's the humility it imposes. Even in our own cosmic backyard, with technology we built ourselves, the universe can still throw us curveballs. The Pioneer Anomaly reminds us that exploration isn't just about the destinations we aim for, but the unexpected detours along the way, and sometimes the smallest deviations lead to the biggest revelations. There's a rule in cosmology so fundamental it's practically gospel. The universe should look the same in every direction. No matter where you point your telescope, the grand tapestry of galaxies, radiation, and emptiness should be statistically uniform, a concept called isotropy. That's why the discovery of the so-called axis of evil sent shockwaves through astrophysics. Hidden in the afterglow of the Big Bang itself, scientists found a pattern so peculiar it seemed to point a finger at one specific direction in space, as if the cosmos had quietly scribbled a secret into its oldest light. This cosmic fingerprint lies in the cosmic microwave background, the faint radiation left over from the universe's infancy. When researchers mapped its temperature fluctuations, the tiny hot and cold spots that seeded all future galaxies, they expected randomness. Instead, they found an eerie alignment. Many of these fluctuations appeared to line up along a particular axis, like invisible threads pulled taut across the sky. Even stranger, this axis seemed to align with the plane of our solar system, a coincidence so statistically unlikely it's like rolling dice 1,000 times and getting the same number every single time. The implications are staggering. If the universe has a preferred direction, it challenges the cosmological principle. the bedrock assumption that no place or orientation in space is special. Some theories scramble to explain it as a fluke, an illusion created by incomplete data or subtle errors in measurement. Others propose more radical ideas. Could the axis be evidence of a pre-Big Bang universe, a shadow of some earlier structure that imprinted itself on our cosmos? Or does it hint at exotic physics, like a primordial magnetic field that stretched space itself into alignment? Then there's the unsettling possibility that we're seeing the handiwork of something beyond our universe. Some theorists speculate the axis might be a bruise left by a collision with another bubble universe during cosmic inflation, a time when space-time expanded faster than light. If true, it would mean our universe isn't just lopsided, it might bear scars from a multiverse we can't yet see. What makes the axis of evil so unnerving isn't just the mystery, it's the way it forces us to confront how much we still don't understand about reality's blueprint. For centuries, we've assumed the cosmos is an even playing field. Now, we're left wondering if the universe has a tilt, a hidden asymmetry written into its very foundations. And until we crack its code, this axis will loom over cosmology like a question mark etched into the fabric of spacetime itself. We think we know what the universe is made of, at least in broad strokes. There's dark energy, dark matter, and then ordinary matter, the stuff that builds stars, planets, and us. But here's the catch: when astronomers tally up all the normal matter they can see, half of it is simply gone. This isn't some exotic substance like dark matter. It's the same protons, neutrons, and electrons that make up everything tangible in existence. And yet, somewhere between the galaxies and the voids, half of it has vanished without a trace. This is the missing Baryon problem, one of cosmology's most persistent accounting errors, and it's forcing us to rethink how matter moves through the cosmic web. The first clues emerged when scientists compared two ways of measuring the universe's ordinary matter. One method looked at the afterglow of the Big Bang, the cosmic microwave background, which reveals how much normal matter should exist based on the universe's early blueprint. The other method counted all the visible matter: stars, gas clouds, galaxies, and the numbers didn't match. Not even close. Nearly 50% of the expected matter was missing, a discrepancy so large it couldn't be brushed aside as measurement error. It was as if the universe had misplaced an entire mountain of its building blocks, leaving us to wonder where they'd been hidden. The leading theory points to the cosmic filaments, those vast, thread-like structures of gas that weave between galaxies, forming a colossal web across the universe. These filaments are thought to contain most of the missing matter in the form of warm hot intergalactic medium, or WIM, a diffuse plasma so hot it's nearly invisible to traditional telescopes. Picture steam rising from a boiling pot. It's there, but unless you catch it at the right angle, you might not notice. The challenge is that WIM doesn't emit much light, and the wavelengths it does release are easily absorbed by Earth's atmosphere or drowned out by brighter cosmic signals. Recent breakthroughs, however, are starting to shed light literally on this elusive material. By using distant quasars as cosmic flashlights, astronomers have detected faint absorption lines in their light, signatures of the WIM tenuous gas. X-ray telescopes have also spotted hints of it in the halos around galaxies, where the gas is slightly denser and hotter. But even with these detections, the numbers still don't fully add up. The filaments might explain some of the missing matter, but not all of it, leaving a gap that suggests our maps of the cosmic web are still incomplete. What makes this mystery so fascinating isn't just the hunt for hidden matter. It's what it reveals about how the universe structures itself. If the missing baryons are indeed hiding in these faint filaments, it means the cosmic web isn't just a backdrop. It's a dynamic, ever-shifting highway for matter, channeling gas across unimaginable distances. Some of that gas might eventually collapse into galaxies, while other strands could remain diffuse, drifting in the darkness for billions of years. Yet the puzzle deepens when we consider alternatives. Could some of the missing matter have been ejected into intergalactic space by supernova explosions or black hole jets? Might it exist in forms we haven't yet imagined, like rogue planets or cold, dark clouds too faint to detect? Every possibility forces us to stretch our understanding of how matter behaves on the largest scales. The missing Baryon problem is more than a cosmic accounting glitch. It's a reminder that even the ordinary can become extraordinary when it slips just out of sight. Until we find every last proton, the universe's ledger remains unbalanced, and with it, our grasp on where and what we truly are in the grand scheme of things. For decades, rumors have swirled about an object silently circling our planet, not a modern satellite or piece of space junk, but something far older, far stranger. Meet the Black Knight, a shadowy presence said to have orbited Earth for thousands of years, long before humans ever dreamed of launching technology into the void. Stories claim it's an alien probe, an ancient artifact, or even a relic from a lost civilization. But is there any truth to these tales, or is the Black Knight just another cosmic ghost story wrapped in static and speculation? The legend began in the 1950s when newspapers reported anomalous radio signals supposedly intercepted by both amateur operators and government listening posts. Some claimed these signals originated from an unknown object in polar orbit, a trajectory unusual for early human satellites. Then came the grainy photographs, shadowy shapes captured during early space missions, often dismissed as debris or camera artifacts, but seized upon by conspiracy theorists as proof of something far more extraordinary. The most famous image, allegedly taken during a 1998 space shuttle mission, shows a jagged, asymmetrical object unlike any known spacecraft. Skeptics point out it's likely a dropped thermal blanket, but believers see something else entirely, a craft not of this world. What fuels the mystery is the sheer persistence of the myth. Unlike most space conspiracies, the Black Knight story stretches back further than the space age itself. Some trace its origins to Nikola Tesla, who in 1899 claimed to have intercepted strange, repeating signals he thought might be extraterrestrial in origin. Others connect it to medieval reports of a dark star seen crossing the sky, an object that couldn't have been a comet or meteor based on historical descriptions. Even ancient astronaut theorists weigh in, suggesting the satellite could be a remnant of an advanced prehistoric culture or a monitoring device left by visitors from the stars. The scientific community, unsurprisingly, remains unconvinced. Every piece of evidence has a plausible earthly explanation, those eerie radio signals. Probably pulsars, natural cosmic beacons that weren't fully understood at the time. The photographs misidentified space debris like discarded rocket parts or insulation fragments. As for the idea of a 12,000-year-old satellite, orbital mechanics makes that impossible. Any unpowered object would have fallen back to Earth long ago due to atmospheric drag. Even the name Black Knight appears to be a modern invention, possibly cobbled together from mid-century military jargon and pop culture. Yet the legend endures, and perhaps that's the real mystery. In an age where we can track every soda can-sized piece of space junk, why does the idea of an ancient satellite still captivate us? Maybe it's the thrill of the unknown, the tantalizing "what if" that lingers at the edge of our high-tech certainty. Or maybe it's something deeper, a reminder that even in our own orbital backyard, there are still stories waiting to be unraveled. Whether the Black Knight is a mirage or something more, its legend continues to orbit not just Earth but our collective imagination. On October 19, 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, an object moving so fast it couldn't possibly be bound by the sun's gravity. Telescopes swiveled to capture it, and what they saw defied every expectation. Named Oumuamua Hawaiian for scout or messenger from afar, this visitor from another star system wasn't just the first of its kind ever detected. It was unlike anything we'd seen before. Shaped like a cosmic cigar, tumbling end over end and glowing faintly reddish under observation, it passed through our neighborhood in a matter of weeks before vanishing back into the void. But the real shock came when researchers realized something impossible was happening. Oumuamua wasn't just coasting, it was accelerating. This wasn't just unusual, it was unprecedented. Natural objects in space slow down or maintain speed unless acted upon by an outside force, like a comet outgassing material as it's heated by the sun. But Oumuamua showed no visible tail, no coma of gas or dust, nothing to explain its sudden speed boost. The lack of outgassing was especially baffling because without it, there was no obvious mechanism for the acceleration. Some scientists proposed exotic explanations, like hydrogen ice sublimating invisibly or even radiation pressure from sunlight, though the latter would require an object far thinner and lighter than any known asteroid. Others pointed to the possibility of microscopic dust ejected at high velocity, too faint for our telescopes to catch. But every theory had holes, leaving researchers with more questions than answers. Then came the suggestion that split the scientific community. Could Oumuamua be artificial? The idea wasn't entirely fringe. Its peculiar shape, roughly 10 times longer than it was wide, bore no resemblance to the lumpy asteroids or icy comets we're familiar with. Its brightness also varied dramatically as it tumbled, suggesting an irregular, possibly flat surface unlike the rougher textures of natural space rocks. Most striking of all was its trajectory. Oumuamua didn't just wander into our solar system by chance. Its path hinted it might have been deliberately aimed, passing close enough to the sun to use its gravity as a slingshot, a maneuver often considered in theoretical designs for interstellar probes. Of course, extraordinary claims demand extraordinary evidence, and most astronomers remain skeptical. The universe is vast, and weird objects likely exist that don't fit our current models. Oumuamua could simply be a fragment of a shattered planet, ejected from another star system in a cataclysmic collision, shaped by forces we've never witnessed. Or perhaps it's the first example of an entirely new class of interstellar objects, one that will make sense only after we've spotted more like it. Yet the mystery lingers because Oumuamua left us so little to study. By the time we noticed it, it was already racing away, carrying its secrets beyond our reach. Future telescopes, like the Vera Rubin Observatory, may spot more interstellar visitors, giving us a better understanding of what's out there. But for now, Oumuamua remains a tantalizing enigma, a cosmic postcard we barely had time to read before it vanished, leaving us to wonder who or what might have sent it. Deep in the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, telescopes have picked up something that shouldn't be there, a faint but persistent glow of gamma rays radiating from the Milky Way's core. Dubbed the Galactic Center Excess, this mysterious signal isn't just background noise. It's too energetic, too perfectly distributed, and most baffling of all, it doesn't match any known astrophysical source. Imagine standing in a darkened room, shining a flashlight at the walls, only to notice an eerie, uniform light coming from nowhere and everywhere at once. That's the puzzle astronomers face when they stare into the galactic center and find this inexplicable hum of high-energy photons. At first, researchers thought they might be seeing the collective glow of thousands of spinning neutron stars called pulsars, or perhaps the aftermath of cosmic rays colliding with gas clouds. But when they mapped the excess, the distribution was all wrong. Pulsars would cluster unpredictably, while this gamma-ray fog spread smoothly across hundreds of light years, like butter smeared evenly over cosmic toast. Then came the tantalizing possibility: what if we're witnessing dark matter annihilating itself? According to some theories, when these invisible particles collide, they could produce gamma rays as a byproduct. The galactic center, with its immense gravitational pull, would naturally concentrate dark matter, making it the perfect place to spot such rare interactions. It's a compelling idea, one that could finally crack the code of the universe's most elusive substance. Yet not everyone's convinced. Skeptics point out that the signal lacks the sharp edges or energy, smoking gun, you'd expect from dark matter. Others argue it might stem from something far more mundane, like a population of faint, fast-spinning stars called millisecond pulsars, or even the remnants of ancient supernova we've yet to catalogue. The debate rages because the answer isn't just about explaining a weird glow. It's about rewriting our understanding of the galaxy's engine. If it's dark matter, we're on the brink of a breakthrough. If it's something else, we've uncovered a cosmic process no one predicted. What makes this mystery so gripping is how it forces us to confront the limits of our tools. The galactic center is a notoriously tricky place to study, hidden behind thick curtains of dust that block visible light. Gamma rays pierce through, but teasing apart their origins is like listening to a symphony where every instrument plays the same note. New telescopes, like the upcoming Cherenkov Telescope Array, promise sharper vision, but for now, the excess remains a riddle wrapped in radiation. It's a reminder that sometimes the most profound discoveries begin with nothing more than a faint, stubborn light, one that refuses to be ignored. Most nebulae in the cosmos are swirling, chaotic masterpieces, great clouds of gas and dust painted across space by stellar winds and explosions. Then there's the Red Rectangle, a cosmic oddity so precise it looks like it was drafted with a ruler. Floating about 2,000 light-years away in the constellation Monoceros, this bizarre structure defies everything we know about how dying stars sculpt their surroundings. Instead of the usual wispy tendrils or billowing spheres, the Red Rectangle presents a near-perfect geometric form, with two blazing cones of gas intersecting to create an X-shape so sharp it could pass for an alien signpost. At the heart of this mystery lies HD 44179, an aging star in its death throes. Like many sun-like stars nearing the end of their lives, it's shedding its outer layers, creating a glowing envelope of ejected material. But here's where the normalcy ends. Instead of forming a messy planetary nebula, the typical fate for such stars, the expelled gas has arranged itself into this uncanny symmetrical structure. Even more puzzling, the entire nebula is nested inside a larger, rectangular frame of reddish dust, giving the object its name and amplifying its otherworldly appearance. It's as if the star took its final bow on a cosmic stage meticulously built for the occasion. Theories abound, but none fully explain the rectangle's precision. One leading idea suggests the star isn't alone, that an unseen companion, perhaps a dense white dwarf or even a small black hole, orbits close enough to shape the outflowing gas into these crisp angles. Think of it like a garden sprinkler spinning rapidly, its jets forming a perfect cone. But even that doesn't account for the nested rectangles or the vibrant red hue, which stems from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons. These complex organics, normally found in the sooty aftermath of combustion, shouldn't survive long in the harsh environment around a dying star, yet here they thrive, painting the nebula in shades of crimson. Then there's the wild card, Could the Red Rectangle be showing us something entirely new about how matter organizes itself in space? Some researchers point to the possibility of magnetic fields, twisted into unprecedented configurations by the dying star's rotation, acting like invisible scaffolding for the gas. Others wonder if we're witnessing the aftermath of a stellar collision, where the debris settled into this improbable form through some poorly understood physics. Even the nebula's spectral fingerprints are odd, with emission lines that don't match any known atomic or molecular transitions, a spectroscopic enigma that's persisted for decades. What makes this object so captivating isn't just its strangeness, it's the way it forces us to reconsider the boundary between chaos and order in the universe. We're used to nature favoring asymmetry, from the spiral arms of galaxies to the branching veins of a leaf. The Red Rectangle, with its razor-sharp lines and nested frames, feels almost artificial by comparison. And while no serious scientist suggests it's a cosmic art project, its very existence whispers a tantalizing truth. There are still forces and processes at work in the universe that we haven't even begun to imagine. Every time we point a telescope at this crimson geometric wonder, it's like staring into a mirror that reflects not just light, but the limits of our own understanding. Imagine a structure so vast it makes entire superclusters of galaxies look like specks of dust. The Hercules-Corona Borealis Great Wall isn't just big, it's universe-redefining big. Stretching an astonishing 10 billion light-years from end to end, this megastructure is the largest known arrangement of galaxies ever discovered, a cosmic behemoth so immense it shouldn't exist under our current understanding of the universe. To put that in perspective, if you could travel at the speed of light, it would take you twice the age of Earth just to cross it. And yet, there it is, a sprawling filament of galaxies, galaxy clusters, and dark matter, threading through the constellations of Hercules and Corona Borealis like a bridge across eternity. What makes this discovery so revolutionary isn't just its size, it's the way it shatters one of cosmology's most fundamental assumptions, the cosmological principle. This idea states that on large enough scales, the universe should look roughly the same everywhere, with matter evenly distributed like raisins in a loaf of bread. But the Great Wall defies that. It's a glaring exception, a cosmic "you missed a spot," that forces us to question whether the universe is as uniform as we thought. How could gravity have pulled together such an enormous structure in the roughly 13.8 billion years since the Big Bang? Even with dark matter's helping hand, the math strains credibility. One theory suggests the Great Wall might be a relic of the universe's infancy, a fossil imprint from when spacetime was still seething with quantum fluctuations. These tiny ripples, magnified by inflation, could have seeded regions where matter clumped more densely, eventually growing into this unimaginably vast ribbon of galaxies. Others propose an even wilder idea, that what we're seeing isn't one structure at all, but the intersection of multiple cosmic filaments, a knot in the universe's web so dense it tricks our telescopes into seeing a single entity. Then there's the unsettling possibility that our models of cosmic evolution are incomplete. Could dark energy, the mysterious force accelerating the universe's expansion, have played a role in sculpting such megastructures? Or might there be unknown physics at work, some primordial asymmetry that funneled matter into these unimaginably large patterns? The Great Wall doesn't just challenge our theories, it holds up a mirror to our ignorance, revealing how much we still don't understand about the universe's architecture. What's equally fascinating is how we found it. The Great Wall lurks in data from gamma-ray bursts, the universe's most powerful explosions. These fleeting flashes act like cosmic lighthouses, and their distribution revealed an eerie concentration, a wall of galaxies so massive it deflects the paths of these bursts like a mountain bending the wind. Yet even now, mapping its full extent is like trying to trace the outline of a continent while standing on its shore. Our telescopes can only see so far, leaving us to wonder, is the Hercules-Corona Borealis Great Wall unique, or is it just the first of many such titans waiting to be discovered? In the end, this colossal structure isn't just a scientific curiosity, it's a cosmic wake-up call. The universe, it seems, still has the power to astonish us with structures so grand they rewrite the rules. And as we peer deeper into the void, who knows what other walls we might find, each one a testament to the universe's endless capacity for wonder. In the quiet hum of radio telescopes scanning the cosmos, astronomers recently stumbled upon something that defies both expectation and explanation: colossal rings of radio energy, so vast they could swallow entire galaxies, yet so faint they'd gone unnoticed for decades. These are odd radio circles, or mysterious celestial halos that glow only in the radio spectrum, invisible to optical, X-ray, or infrared telescopes. Picture a smoke ring blown by a giant, but scaled up to millions of light years across, floating in the depths of space with no obvious source or cause. Since their discovery in 2020, these ghostly circles have become one of the most perplexing puzzles in modern astronomy, precisely because they shouldn't exist. What makes ORCs so baffling is their eerie perfection. Unlike the chaotic aftermath of a supernova or the twisted jets of a black hole, these structures are strikingly symmetrical, as if drawn with a cosmic compass. They don't encircle any visible galaxy or cluster, ruling out straightforward explanations like shockwaves from stellar explosions. Even more puzzling, some ORCs contain galaxies at their centers, but those galaxies show no signs of unusual activity. No bursts of star formation, no feeding supermassive black holes, nothing that could explain the titanic energy required to sculpt such rings. It's like finding a perfectly carved stone monument in the desert, with no evidence of the civilization that built it. Theories range from the dramatic to the downright speculative. One leading idea suggests ORCs might be the aftermath of a starburst tsunami, a cataclysmic wave of star formation so intense it sent shockwaves rippling through intergalactic gas, leaving these radio echoes behind. Another proposal points to dark galaxies, hypothetical structures rich in dark matter but devoid of stars, whose gravitational interactions could generate faint radio signals. Then there's the more exotic possibility. ORCs could be the imprint of a wormhole's throat, a tunnel through space-time predicted by some unified physics theories, though admittedly, that's a long shot even for astronomers. Perhaps the most tantalizing clue lies in their timing. ORCs seem to be a relatively recent phenomenon in cosmic terms, with none detected in older radio surveys. This raises the spine-tingling question: are we witnessing a new kind of cosmic event, one so rare it's only now beginning to flicker into visibility? Or have these circles been there all along, hiding in plain sight, waiting for our technology to catch up? Every new observation deepens the intrigue. Some ORCs appear to have faint optical counterparts when examined with the world's most powerful telescopes, while others remain stubbornly invisible in all wavelengths except radio. What's truly exhilarating about these enigmas is how they expose the limits of our cosmic maps. The universe, it seems, still has phenomena up its sleeve that don't fit any existing category. No textbook, no simulation predicted something like ORCs. They're a reminder that for all our advancements, the cosmos retains its capacity to astonish, throwing curveballs that force us back to the drawing board. And as telescopes like the Square Kilometre Array come online, capable of detecting fainter, more distant ORCs, we might finally catch these ghostly rings in the act of forming, revealing the invisible hand that sculpts them. Until then, they drift through the darkness, silent and enigmatic, like messages in a code we've only just begun to crack. Among the countless worlds scattered across the cosmos, few are as dazzling or as perplexing as Quasar J1719-1438b, better known as the Diamond Planet. This extraordinary world orbits a pulsar, the rapidly spinning corpse of a dead star, in a cosmic dance that defies everything we know about planetary formation. But here's the twist: this planet isn't just rich in carbon, it's likely a colossal diamond, a crystallized gem the size of a planet, forged in the aftermath of stellar catastrophe. The story of how this bizarre world came to be reads like a cosmic thriller. Its parent star, a pulsar, is the remnant of a once mighty star that went supernova, leaving behind a dense, city-sized core spinning hundreds of times per second. The intense gravitational pull of this stellar zombie stripped away the outer layers of its orbiting companion, leaving behind a skeleton of carbon and oxygen, elements compressed under unimaginable pressure into a crystalline lattice. Picture a star's corpse spinning furiously, its gravitational claws tearing apart a neighboring world, and what remains is a glittering, Earth-sized diamond adrift in the void. Yet the mystery runs deeper than its composition. How could such a dense, carbon-rich planet survive the supernova explosion that birthed its pulsar host? Most planets in similar situations would have been vaporized or flung into the abyss. One theory suggests the Diamond Planet might have been the core of a gas giant, its outer layers blasted away by the pulsar's radiation, leaving only its crystalline heart behind. Another idea posits it could be the shattered remains of a white dwarf star, its matter crushed into diamond by the pulsar's gravity. Either way, its existence pushes the boundaries of what we thought possible for planetary formation. What's even more tantalizing is what this discovery implies about the universe's hidden diversity. If a diamond planet exists, what other unimaginable worlds might be out there? Planets made of solid metallic hydrogen, perhaps, or worlds where rain falls as liquid gemstones. The pulsar's extreme environment, a crucible of radiation and gravity, might be the factory for exotic worlds we've yet to dream of. And while we'll never set foot on this diamond behemoth, its surface temperatures hover near thousands of degrees, and its gravity would crush a human instantly. Its very existence expands the palette of planetary possibilities. This glittering enigma also raises a provocative question. Could there be other diamond planets orbiting more hospitable stars? Carbon-rich worlds might be more common than we think, hiding in plain sight, their surfaces disguised by layers of hydrocarbon haze or graphite. Future telescopes like the James Webb Space Telescope could sniff out their chemical signatures, revealing whether the universe is littered with such treasures. In the end, the Diamond Planet isn't just a cosmic oddity, it's a testament to the universe's boundless creativity. From the ashes of stellar death, it crafted a world more fantastical than any jewel, a reminder that the cosmos still holds wonders beyond our wildest imagination. And as we keep searching the skies, who knows what other priceless secrets might be waiting to sparkle into view? We might like to think of our cosmic neighborhood as typical, just another unremarkable corner of an infinite universe. But the KBC Void suggests otherwise. We could be floating inside one of the largest cosmic anomalies ever discovered, named after astronomers Keenan, Barger, and Cowie, who first mapped its staggering dimensions. This underdense region stretches over 2 billion light-years across, with the Milky Way sitting near its center like a speck in a vast, hollowed-out bubble. And its existence throws a wrench into one of cosmology's most cherished assumptions, that the universe looks roughly the same everywhere when you zoom out far enough. What makes the KBC Void so unsettling isn't just its size, it's the sheer scarcity of matter within it. While most of the universe clusters into a web of galaxies and filaments, this void is eerily empty, with densities up to 20% lower than average. To put that in perspective, if the cosmos were an ocean, we'd be adrift in a desert island of near-nothingness, surrounded by distant shores of vibrant galactic activity. The odds of such a void existing by chance, astronomers estimate less than 1 in 100. It's as if the universe rolled a pair of dice and landed on snake eyes over and over, defying probability itself. This raises a provocative question. Could the KBC Void explain one of cosmology's most stubborn discrepancies, the Hubble tension? Measurements of the universe's expansion rate disagree depending on whether we use nearby supernova or the cosmic microwave background. But if we're inside a local underdensity, gravity's weaker pull here might be subtly accelerating our region's expansion, skewing the numbers. Think of it like standing in a valley while trying to gauge the slope of a mountain. Your perspective is inherently warped by your position. The void could be that valley, tricking us into seeing the universe's expansion as faster than it truly is elsewhere. Yet not all scientists are convinced. Some argue the void's apparent emptiness might be an illusion, a trick of incomplete observations where dust or foreground galaxies obscure our view. Others propose even wilder explanations, like exotic physics or primordial fluctuations frozen into the fabric of space-time during the Big Bang. Then there's the existential implication. If we do live in a bubble, how many others like it might exist? Could the universe be a patchwork of overdensities and voids, each with their own unique, local physics? The KBC Void forces us to confront the unnerving possibility that our cosmic address might not be as ordinary as we once thought. What's truly humbling is how this discovery reframes our place in the grand scheme. For centuries, we clung to the idea that Earth held no special position in the universe, a principle called the Copernican principle. But the KBC Void whispers a tantalizing exception. While we may not be at the center of everything, we might still be somewhere profoundly unusual. Every time astronomers peer deeper into its emptiness, they're not just mapping a void, they're testing the very foundations of cosmology, probing whether our universe is as uniform as we've always assumed. And until we find answers, this billion-light-year pocket of nothingness will keep staring back at us, silent and enigmatic, a cosmic hall of mirrors where the reflection might just change everything. Hidden in the cosmic shadows just 1,500 light-years away, astronomers have found something that shouldn't exist, a black hole so small, so quiet, it's practically a ghost. Meet the unicorn, a celestial oddity tipping the scales at just 3 times the mass of our Sun, making it one of the tiniest black holes ever detected. What makes this discovery so extraordinary isn't just its size, it's the way it lurks undetected, warping the orbit of a nearby red giant star like an invisible puppeteer, all while emitting no light, no radiation, nothing but the faintest gravitational whisper. Black holes this small occupy a mysterious gap in our cosmic inventory. Theory predicts they should form when massive stars collapse, but most known black holes are heftier, starting around 5 solar masses. The unicorn, however, slips into a theoretical sweet spot, the lower limit of what's possible before a dying star becomes a neutron star instead. Its very existence suggests there could be countless others like it, a hidden population of diminutive black holes drifting unseen through the galaxy. Think of them as cosmic stealth fighters, cloaked by their very nature, detectable only when they interact with another star. The hunt for the unicorn began with a subtle anomaly. Astronomers noticed its companion star, a red giant, was being stretched and squeezed by an unseen force, its light rhythmically dimming and brightening as if tugged by an invisible partner. By mapping these distortions, researchers pieced together the presence of a compact object, one too dense to be a neutron star, yet too small to fit the typical black hole mold. It's like hearing the faintest footsteps in an empty room and realizing something invisible is sharing the space with you. This discovery cracks open a new frontier in stellar astrophysics. If the unicorn isn't alone, it could mean that small black holes are far more common than we thought, lurking in binary systems where they've evaded detection. Some scientists speculate these could be primordial black holes, forged in the chaos of the Big Bang rather than from dying stars. Others wonder if they're the missing link in black hole evolution, a bridge between neutron stars and their heavier cousins. Either way, their presence would rewrite the story of how stars live, die, and leave their marks on the universe. What's truly thrilling is how the unicorn forces us to rethink our tools. Traditional black hole hunting relies on spotting X-rays from their accretion disks, but tiny black holes like this one, with no nearby material to consume, slip through the net. New techniques like tracking the subtle wobbles of companion stars might be the key to uncovering more of these cosmic phantoms. And with every new detection, we edge closer to answering one of astronomy's most haunting questions: just how many invisible giants are hiding in plain sight? The unicorn isn't just a scientific curiosity, it's a beacon, illuminating the gaps in our understanding of the universe's darkest residents. Its quiet existence whispers a tantalizing truth. Sometimes the most profound discoveries aren't made by what we see, but by what we barely sense. And as our methods grow sharper, who knows how many more of these elusive shadows might step into the light? Most galaxies are glittering metropolises of stars, their spiral arms or elliptical halos shining brightly across the cosmos. But Dragonfly 44 is different, a phantom city where the lights are almost all off. Discovered in 2016 lurking in the Coma cluster, this bizarre galaxy emits just 1% of the light expected for its size, with stars so sparse you could fly through it for light years without seeing a single sun. Yet despite this eerie emptiness, Dragonfly 44 weighs as much as the Milky Way. The reason? It's made almost entirely of dark matter, the universe's most elusive substance, outnumbering normal matter by a staggering ratio of 10,000 to 1. This isn't just a galaxy with some dark matter. It's a dark galaxy, a cosmic paradox that shouldn't exist under our current models, yet here it is, silently rewriting the rules of galactic evolution. What makes Dragonfly 44 so unsettling is how it defies the standard recipe for galaxy formation. Normally, dark matter acts as a scaffold, its gravity pulling gas and dust together until stars ignite. But in this case, something went wrong, or perhaps something we don't yet understand went right. The galaxy's few stars move at dizzying speeds, orbiting so fast they should have been flung into the void long ago. The only thing holding them in place is the immense gravitational grip of an unseen dark matter halo, a shadowy cocoon with 99.99% of the galaxy's mass. It's like finding a car speeding down the highway with no engine, only to realize invisible hands are pushing it forward. Theories about how such ghosts form range from the violent to the sublime. One possibility is that Dragonfly 44 was once a normal galaxy, its stars stripped away by tidal forces as it plunged through the crowded Coma cluster, leaving behind only its dark matter skeleton. Another idea suggests it's a failed galaxy, a patch of the early universe where gas never quite condensed enough to birth many stars, leaving its dark matter to dominate uncontested. Then there's the wild card. Could dark galaxies be the universe's hidden architects, their gravity subtly shaping the cosmic web in ways we've only begun to detect? The implications ripple far beyond this single ghostly structure. If Dragonfly 44 isn't alone, if the cosmos is peppered with similar dark galaxies, it could explain why the universe's missing Baryon problem persists. These shadowy giants might be hoarding vast reservoirs of normal matter in forms too faint or diffuse for our telescopes to spot. They could also serve as dark matter laboratories, their extreme ratios offering clues to how this mysterious substance interacts with itself and the rest of the cosmos. Yet the greatest mystery isn't how dark galaxies exist, it's why they're so rare. For every Dragonfly 44, there are thousands of bright, star-filled galaxies. Does this mean dark galaxies are cosmic accidents, or are we just terrible at finding them? New telescopes like the Vera Rubin Observatory may soon reveal more of these phantoms, hiding in plain sight all along. Until then, Dragonfly 44 remains a tantalizing enigma, a galaxy that shines not by the light it emits, but by the questions it forces us to ask. At the heart of the Virgo cluster, 55 million light-years away, a cosmic titan feasts in the darkness. Messier 87 isn't just any galaxy, it's a galactic cannibal, a monstrous elliptical beast whose supermassive black hole weighs in at a staggering 6.5 billion times the mass of our Sun. But what makes M87 truly terrifying isn't just its size, it's the way it devours everything around it with an appetite that defies reason. Stars, gas clouds, even entire galaxies all get shredded into a swirling banquet of plasma before vanishing beyond the event horizon, fueling the most energetic processes in the known universe. The evidence of this feeding frenzy is etched across the galaxy in strokes of violence. Hubble's Space Telescope images reveal a jet of superheated plasma shooting 5,000 light-years into space, a relativistic blowtorch powered by the black hole's insatiable hunger. This jet moves at nearly the speed of light, twisting magnetic fields so intense they act like cosmic particle accelerators, hurling radiation across the cosmos. Meanwhile, the black hole's accretion disk, the swirling maelstrom of doomed matter, glows brighter than all the stars in M87 combined, a telltale sign of a meal in progress. It's as if the galaxy itself is built around this ravenous engine, its entire structure warped by the black hole's gravitational dominance. What's truly baffling is the scale of this consumption. Most supermassive black holes nibble at their surroundings, occasionally flaring when a star drifts too close. But M87's black hole feasts continuously, as if the galaxy itself is funneling material toward it like a cosmic conveyor belt. Astronomers suspect this relentless feeding stems from the galaxy's violent history. Over billions of years, M87 has cannibalized dozens of smaller galaxies, their stars adding to its halo while their gas spirals inward, feeding the beast at its core. This isn't just a black hole, it's the product of an entire ecosystem built on destruction, a galactic Ouroboros forever consuming itself. Yet the most revolutionary discovery came in 2019, when the Event Horizon Telescope unveiled the first ever image of this monster's shadow. That iconic orange ring, a lensed image of photon orbits around the event horizon, confirmed Einstein's wildest predictions, but it also raised new questions. Why is M87's black hole so unusually active compared to others of similar size? Some theorists point to the galaxy's lack of star formation. With little newborn starlight to compete, the black hole's glow dominates. Others suggest its spin plays a role, twisting spacetime itself into a vortex that drags matter inward more efficiently. Then there's the dark matter factor. could invisible halos be guiding extra material toward the center like cosmic cattle chutes? The implications ripple far beyond a single galaxy. If M87's black hole is a template for how galactic cores evolve, it could explain why some galaxies die, their star-making fuel siphoned away by central black holes. It might also hint at how the universe's largest structures grow, with black holes acting as gravitational anchors that shape entire clusters. Every new observation peels back another layer, revealing a universe where the most violent forces are also the most creative, where destruction and rebirth spiral together in an endless cosmic dance. As we stare into the maw of this celestial predator, we're not just witnessing a black hole's meal, we're seeing the universe's raw power unveiled. M87 doesn't just defy expectations, it forces us to rethink the very nature of gravity, time, and the invisible threads that bind galaxies together. And somewhere in its furious glow, there might be answers to the greatest mystery of all: how darkness shapes the light. Dark energy was supposed to be the universe's most boring ingredient, a constant, unchanging force steadily pushing space itself apart. But what if it's not? What if this mysterious energy, making up 68% of the cosmos, is actually shifting over time, growing stronger or weaker like a cosmic tide we can barely measure? That's the startling possibility raised by recent observations of distant supernova, galaxy clusters, and quasars data that hints dark energy might not be the cosmological constant Einstein imagined, but something far stranger. If confirmed, this phantom-like variability could upend everything we thought we knew about the universe's fate, turning a slow, cold expansion into something far more dramatic. The first whispers of this anomaly came from subtle mismatches in the cosmic distance ladder. When astronomers measure how fast the universe is expanding using different techniques, supernova, Baryon acoustic oscillations, the cosmic microwave background, they should get the same answer. But they don't. Some methods suggest the expansion is accelerating faster than expected, as if dark energy's push has grown stronger over billions of years. Other datasets show the opposite, hinting at a weakening force. The discrepancies are small, but in cosmology, even tiny inconsistencies can signal a seismic shift. It's like noticing the ocean's tide rising slightly higher each year, a clue that the moon's pull might not be as steady as we assumed. One explanation for these phantom fluctuations lies in quintessence, a theoretical form of dark energy that evolves over time. Unlike the static cosmological constant, quintessence could interact with itself or other forces, diluting or concentrating its energy as the universe ages. Picture a pot of water slowly boiling away. The steam's pressure changes as the liquid diminishes. If dark energy behaves similarly, its repulsive force might have been weaker in the early universe, only to dominate later as matter thinned out. Some models even suggest it could one day reverse, collapsing the cosmos in a big crunch rather than an eternal expansion. Then there's the elephant in the room. Could varying dark energy be a sign we've misunderstood gravity itself? Modified gravity theories, like more sophisticated cousins, propose that Einstein's equations break down on cosmic scales, making it seem like an invisible force is at work when in reality, space-time bends differently than we thought. It's a radical idea, one that would require rewriting the textbooks, but if dark energy's variations are actually the fingerprints of a deeper gravitational law, the implications would be staggering. What makes this mystery so urgent is its existential stakes. If dark energy strengthens, it could eventually tear apart galaxies, then stars, and finally atoms in a big rip. If it fades, gravity might regain dominance, halting expansion or even reversing it. And if it oscillates, the universe could pulse like a living thing, cycling between expansion and contraction. We're not just talking about tweaking equations, we're grappling with the ultimate fate of reality itself. The challenge now is untangling signal from noise. Is the phantom dark energy real, or are we seeing systematic errors in our measurements? Future telescopes like the Vera Rubin Observatory and ESA's Euclid mission will map billions of galaxies, hunting for patterns that could confirm or crush these tantalizing hints. Until then, the cosmos holds its cards close, leaving us to wonder, are we witnessing the first cracks in our cosmic model, or just the growing pains of a deeper truth coming into focus? Deep in the cosmic dawn, when the universe was just 5% of its current age, a monster was already awake. Ulas J1342 plus 0928 isn't just any quasar. It's a time-defying paradox, a supermassive black hole weighing in at 800 million suns, shining with the brightness of 1 trillion stars, all while the cosmos itself was still in its infancy. At just 690 million years old, this behemoth shouldn't exist. According to everything we know about black hole growth, there simply wasn't enough time after the Big Bang for gravity to gather and compress matter into something so colossal. Yet there it is, blazing across 13 billion light-years of space, its very existence tearing at the seams of our understanding. The puzzle lies in the math. Black holes grow by feeding on gas, dust, and stars, but even under ideal conditions, there's a speed limit to how fast they can devour their surroundings. Known as the Eddington limit, this rule states that as a black hole consumes matter, the resulting radiation pushes back, creating a balance that prevents infinite gluttony. To reach 800 million solar masses so quickly, Ulas J1342 would have needed to break this rule consistently, feasting at nearly maximum capacity for its entire existence, a scenario so unlikely it's like rolling 1,000 dice and getting sixes every single time. So how did this cosmic overachiever cheat the system? One radical theory suggests the universe might have birthed seed black holes far larger than we ever imagined. Instead of forming from collapsed stars, which max out at a few dozen solar masses, these primordial seeds could have been born supermassive from the start, condensing directly from dense patches of gas in the early universe. Picture a cosmic shortcut where gravity skipped the usual steps and went straight to building giants. Another possibility is that the first black holes grew through runaway collisions in incredibly crowded stellar nurseries, merging over and over like snowballs rolling downhill. But the most mind-bending explanation involves dark matter. Some models propose that certain types of this mysterious substance could have interacted with early black holes in ways we don't yet understand, supercharging their growth like invisible fertilizer. It's a tantalizing thought that the very fabric of the universe's unseen scaffolding might have played midwife to these impossible monsters. What makes this quasar so transformative isn't just its size, it's the way it forces us to rethink the universe's first chapters. If black holes could grow this big, this fast, the early cosmos might have been far more dynamic and chaotic than our simulations suggest. Galaxies could have formed inside out, with black holes appearing first and stars assembling around them like moths to a flame. The faint afterglow of the Big Bang might hide other surprises, echoes of an era when the rules of physics played by a different script. Every photon from Ulas J1342 is a messenger from that forgotten age, carrying clues to how darkness first took hold in the universe. And as our telescopes probe deeper into the cosmic dawn, we might just find that this impossible quasar isn't alone, that the early universe was a place where monsters didn't just lurk in the shadows but built them. Between the glittering islands of galaxies, the universe hides its scaffolding, vast, invisible threads of gas stretching millions of light years, weaving the cosmos into a single connected tapestry. This is the cosmic web, the grand architecture of reality itself, where dark matter's gravity sculpts rivers of hydrogen so diffuse they're nearly impossible to see. Theory predicts these filaments should be everywhere, channeling matter across the void, fueling galaxy growth like roots feeding a forest. Yet when astronomers train their telescopes on the spaces between galaxies, they find eerie silence. Where are these missing links, and why does the universe seem to be hiding its own blueprints? The hunt begins with the basics. What should these filaments look like? Simulations show the cosmic web as a labyrinth of tendrils, with galaxies clustered at the intersections like dewdrops on a spider's web. The filaments themselves are thought to be mostly hydrogen gas, heated to temperatures between 10,000 and 10 million degrees, too cool to glow brightly in X-rays, too hot to form detectable clouds. Spotting them requires ingenuity, like trying to map a city's power grid by photographing only the streetlights. Astronomers have had glimpses, faint absorption lines in the light of distant quasars, or the shimmer of the Sunyaev-Zeldovich effect distorting the cosmic microwave background. But these are shadows of shadows, hints rather than portraits. One breakthrough came with the discovery of the Lyman Alpha Forest, a strange pattern in quasar light where hydrogen filaments absorb specific wavelengths, creating a barcode of missing light across the spectrum. Each line represents a filament crossed by the quasar's beam, a single thread in the web. But even this technique reveals only the densest strands, leaving the majority uncharted. Another approach uses gravitational lensing, where the filament's mass bends light from background galaxies like a funhouse mirror. Here, too, the signal is maddeningly faint, like trying to hear a whisper in a hurricane. The implications of these missing links ripple far beyond cartography. If the filaments are fainter or sparser than predicted, it could mean our models of gas accretion, how galaxies siphon fuel from the cosmic web, are fundamentally flawed. Perhaps the gas is clumpier than simulations suggest, or maybe magnetic fields and turbulence shred the filaments into undetectable fragments. There's even a radical possibility that the missing gas isn't missing at all, but hiding in plain sight as ultra-diffuse plasma, a mist so fine it evades every observational net we've cast. What's at stake isn't just a census of hydrogen. The cosmic web is the universe's circulatory system, and its filaments are the conduits delivering the raw materials for stars, planets, and life. Without them, galaxies would starve, their growth stunted before reaching maturity. Understanding these hidden highways could explain why some galaxies blaze with newborn stars while others fade into quiet obscurity. It might even shed light on dark matter itself, whose gravitational pull is the unseen hand guiding the web's structure. As telescopes like the James Webb Space Telescope and the upcoming Square Kilometre Array push deeper into the infrared and radio spectrum, the veil may finally lift. Every new detection, every faint filament traced in the darkness, brings us closer to seeing the universe not as isolated islands of light, but as a single, breathing organism connected by threads we're only beginning to glimpse. And when the full map is drawn, we might discover that the missing links were never lost at all, just waiting for us to learn how to see. Deep beneath the Antarctic ice, where sunlight never reaches and temperatures plunge below -50 degrees, an unlikely sentinel stands watch for cosmic ghosts. The Ice Cube Neutrino Observatory isn't hunting for spirits. It's tracking neutrinos, the universe's most elusive particles, so insubstantial they pass through entire planets like smoke through a screen. But in 2013, IceCube caught something extraordinary, a shower of high-energy neutrinos with no obvious source. their origins tracing back to voids between galaxies where nothing should be violent enough to create them. This neutrino excess isn't just a scientific curiosity, it's a cosmic alarm bell, ringing from places the universe has kept hidden until now. Neutrinos are born in extreme environments, supernova explosions, black hole jets, the hearts of collapsing stars. They're nature's ultimate messengers, carrying information across billions of light years without being absorbed or deflected. But the neutrino's ice cube detected pack energies 1,000,000 times greater than those from our sun, suggesting they were forged in conditions far more ferocious than anything we've witnessed. The mystery: when astronomers turned telescopes toward the directions these particles came from, they found nothing. No gamma-ray bursts, no flaring quasars. Just empty space, as if the neutrinos had slipped through a crack in reality itself. One leading theory points to Blazar's supermassive black holes whose jets happen to point directly at Earth, potentially accelerating particles to near light speeds. Yet when researchers cross-referenced neutrino detections with known blazars, fewer than half matched up, another suspect is tidal disruption events, where stars are shredded by black holes, creating fleeting but intense bursts of energy. These cosmic demolition derbies could theoretically produce neutrinos, but they're too rare to explain the sheer number of detections. Then there's the possibility of hidden neutron stars with unimaginably strong magnetic fields, acting as natural particle accelerators too faint for our telescopes to spot. But the most tantalizing explanation lies beyond known physics. Some theorists suggest these neutrinos could be byproducts of dark matter annihilation, invisible particles colliding and decaying in the voids between galaxies. Others speculate they might originate from cosmic strings, hypothetical defects in spacetime left over from the Big Bang, vibrating like snapped guitar strings and releasing energy in the form of particles. If true, the neutrino excess isn't just a puzzle, it's a backdoor into understanding forces and phenomena that operate outside the standard model. What makes these ghostly particles so transformative is how they bypass the cosmic censorship that hides so much from our view. Dust clouds, magnetic fields, and sheer distance obscure many of the universe's most violent events. Neutrinos, indifferent to such obstacles, deliver unfiltered dispatches from the front lines of cosmic chaos. Every high-energy neutrino that strikes Ice Cube is a bullet fired from some unseen battlefield, its trajectory a clue to battles raging in the dark. As detectors grow more sensitive, the neutrino excess may soon reveal its secrets or deepen the mystery further. Future upgrades to Ice Cube, along with projects like the Pacific Ocean's KM3 NET, will turn Earth into a giant neutrino telescope, catching these phantoms from every angle. And with each new detection, we edge closer to answering a question that strikes at the heart of astrophysics. What unimaginable engines are lurking in the void, firing bullets of pure energy across the cosmos, and why do they hide from every eye but the neutrinos? The universe, it seems, still has battlefields it hasn't shown us, and soldiers we're only just learning to see. Somewhere in the vast expanse of intergalactic space, a monster is on the loose, a supermassive black hole, weighing as much as 20 million suns, hurtling through the void at 4 million miles per hour. Astronomers first spotted its trail in Hubble images, a bizarre, straight line of young blue stars stretching 200,000 light-years, like cosmic breadcrumbs left behind by something unimaginably powerful. This isn't just a wandering black hole, it's a celestial fugitive, violently ejected from its home galaxy in what must have been one of the most catastrophic events since the Big Bang. The physics behind this cosmic getaway reads like a gravitational thriller. When two galaxies merge, their central black holes eventually spiral together, locked in a dance that ends with a titanic collision. Normally, they merge into a single, larger black hole. But if a third black hole enters the mix, perhaps from a previous galactic merger, the resulting three-body chaos can fling one of them into deep space like a slingshot. That appears to be what happened here. As the black hole was ejected, its immense gravity plowed through clouds of gas, compressing them so violently that new stars ignited in its wake. The result, a stellar jet stream marking the black hole's path like contrails behind a runaway freight train. What's truly baffling is the scale of the forces involved. To accelerate a 20 million solar mass object to such speeds would require energy equivalent to 100 million supernova exploding in perfect unison. The fact that we're seeing this at all suggests these extreme recoil events might be more common than we thought, hidden drivers reshaping the cosmic landscape in ways we're only beginning to recognize. Some theorists even speculate that rogue black holes could be lurking throughout intergalactic space, invisible except for the faint trails of stars they might leave behind. The implications rewrite our understanding of galactic evolution. If supermassive black holes can be ejected so easily, some galaxies might lack central black holes entirely, or harbor ones that are still wobbling from ancient collisions. It also raises eerie questions about what else might be drifting undetected in the darkness. Could there be black holes wandering between galaxies, their paths marked only by the occasional twinkle of newborn stars? Future telescopes like the Nancy Grace Roman Space Telescope could hunt for these stellar trails, mapping the invisible highways carved by history's most violent breakups. For now, this runaway black hole remains a singular spectacle, a reminder that even the universe's most massive objects aren't anchored forever. Galaxies collide, black holes duel, and sometimes the losers get thrown into the void, trailing starlight like cosmic graffiti. And as we trace its path back to the scene of the crime, we're left to wonder, what other gravitational dramas are unfolding in the darkness, waiting for us to stumble upon their aftermath? Most galaxies are like living things, constantly changing, merging, and evolving over billions of years. But NGC 1277 didn't get the memo. This ancient relic, floating in the constellation Perseus, looks exactly as it did 10 billion years ago, a fossilized snapshot of the early universe frozen in time. While other galaxies grew fat on cosmic gas or collided in spectacular mergers, this one stayed stubbornly unchanged, a celestial hermit that rejected the universe's relentless march of progress. And the most baffling part, it shouldn't exist. At the heart of this cosmic time capsule lies a mystery wrapped in starlight. Unlike modern galaxies, where stars come in all ages, some newborn, others ancient, NGC 1277 is a monochromatic sea of old red stars. Not a single young blue star flickers in its disk, no spiral arms twist with fresh stellar nurseries. It's as if the galaxy hit pause shortly after forming and never pressed play again. Even stranger, its central black hole is grotesquely oversized, weighing in at 17 billion suns, one of the most massive ever discovered relative to its host galaxy. That mismatch defies everything we know about how black holes and galaxies grow together, like finding a toddler with the muscles of a gorilla. Theories about how this anomaly survived unscathed range from the unlucky to the bizarre. One idea suggests it was born in a cosmic desert, a region so devoid of gas that it couldn't form new stars even if it wanted to. Another proposes it was ejected from its galaxy cluster early on, flung into the void where no mergers could disturb its solitude. Then there's the dark horse explanation, that NGC 1277 is the last survivor of a lost population of red nuggets, compact galaxies common in the early universe that should have all evolved or been absorbed by now. If true, it's like stumbling upon a living dinosaur, a relic from an era when the cosmos looked utterly different. What makes this galaxy so transformative isn't just its defiance, it's the questions it forces us to ask. If one such relic exists, could there be others hiding in plain sight, masquerading as ordinary galaxies until closer inspection? Could their untouched chemistry hold clues to the universe's primordial elements, uncontaminated by later cosmic events? And most tantalizing of all, does their existence suggest our models of galactic evolution are missing a crucial piece of physics, some forgotten force or condition that allowed these outliers to opt out of the universe's relentless churn? Every photon from NGC 1277 is a message in a bottle from the cosmic dawn, carrying secrets about how galaxies began and why this one refused to follow the script. As telescopes like the James Webb peer deeper into the past, we might finally learn whether this impossible galaxy is a solitary rebel or the first of many time capsules waiting to rewrite history. Until then, it stands as a silent monument to the universe's enduring capacity to surprise us, proving that even in a cosmos ruled by change, some things refuse to play along. The thin, rust-colored atmosphere of Mars holds a secret, one that pulses in and out of existence like a whisper just beyond hearing. Methane, a gas that on Earth is overwhelmingly tied to life, keeps appearing in the Martian air in fleeting bursts before vanishing without a trace. Since its first detection by the European Space Agency's Mars Express orbiter in 2004, this enigma has taunted scientists with two equally tantalizing possibilities. Is it the signature of hidden geological processes, or could it be the faintest hint that microbial life might still cling to the cracks and shadows of the red planet? What makes methane so intriguing isn't just its biological potential, it's the way it defies expectations. On Earth, most atmospheric methane comes from living organisms, from burping cows to decomposing swamps. But it can also arise from non-living sources like volcanic activity or chemical reactions between water and certain rocks. Mars, with its extinct volcanoes and vast underground ice, could theoretically produce methane either way. The problem: this gas shouldn't linger. Sunlight and chemical reactions in the Martian atmosphere should break it down within a few hundred years, which means whatever's releasing it is doing so right now. The detections aren't just random, they're seasonal, spiking in the northern hemisphere's summer months like clockwork before dissipating. It's as if the planet itself is exhaling on a schedule we don't yet understand. The stakes couldn't be higher. NASA Curiosity rover has sniffed methane repeatedly in Gale Crater, sometimes recording spikes 10 times above background levels. Yet when the ESA's Trace gas orbiter flew overhead with far more sensitive instruments, it found nothing. This discrepancy isn't just frustrating, it's a full-blown scientific whodunit. Could the methane be pooling near the surface in Curiosity's vicinity, only to vanish before orbiters can spot it? Or is the rover itself somehow producing the gas, though engineers have ruled out contamination? The mystery deepened in 2019 when Curiosity detected both methane and oxygen behaving unpredictably in the same location, as if some unseen process were cycling them together. Theories swing between the mundane and the extraordinary. On the geological side, serpentinization, a reaction between water, carbon dioxide, and olivine rock, could produce methane deep underground, with fractures releasing it sporadically. Another idea involves clathrates, icy cages of methane trapped beneath the surface that might destabilize when temperatures rise. But the wild card remains biology. On Earth, methanogen's simple microbes thrive in places devoid of oxygen, like deep underground or in the guts of termites. If similar organisms exist on Mars, eking out an existence in briny subsurface aquifers, they could be belching these methane bursts. The fact that the spikes align with warmer seasons fuels speculation. Could Martian microbes, if they exist, become more active when subsurface ice melts slightly, releasing gases accumulated during colder months? Yet every clue raises new questions. If the methane is biological, why haven't we found other supporting evidence like complex organic molecules? If it's geological, why don't orbiters see hotspots linked to tectonic or volcanic activity? The answer might lie in the planet's hidden plumbing. Mars's subsurface could be a labyrinth of sealed pockets and narrow fissures, allowing gas to seep out in isolated patches rather than global plumes. Or perhaps the methane is being destroyed faster than we think, scavenged by unknown chemical reactions in the Martian soil. The pursuit of this ghostly gas has become a cornerstone of Mars exploration. Future missions like the Rosalind Franklin rover will carry drills capable of digging deeper than ever, probing for subsurface organics. Meanwhile, scientists are rethinking how to track methane's ephemeral traces, debating whether drones or networks of ground-based sensors could catch it in the act. Until then, these sporadic whiffs of methane remain the ultimate cosmic tease, a puzzle wrapped in a riddle, floating in the thin air of a world that refuses to give up its secrets easily. And with every fleeting detection, we're left to wonder, is Mars just a rusty rock with a few odd quirks, or is it hiding something far more extraordinary beneath its barren surface? In the cosmic menagerie of stars, most are predictable, blending hydrogen, helium, and a sprinkle of heavier elements forged in stellar furnaces. But SDSS J102915 plus 172927 isn't most stars. This ancient relic, flickering in the constellation Leo, defies the very laws of stellar physics. Dubbed the impossible star, it's made almost entirely of hydrogen and helium, with heavy elements like carbon and iron nearly 1 million times scarcer than in our Sun. For context, if the Sun were a gourmet meal, this star would be a single grain of salt lost in a football field. And yet, against all odds, it exists, a pristine time capsule from the universe's infancy, challenging everything we thought we knew about how stars are born. The mystery starts with its composition. According to our models, stars like this shouldn't shine at all. Heavy elements, what astronomers call metals, aren't just cosmic seasoning. They're essential for cooling gas clouds enough to collapse into stars. When a cloud fragments, metals radiate heat away, allowing dense pockets to form. Without them, gas stays too hot and diffuse, resisting gravity's pull. Imagine trying to freeze a boiling pot of water by blowing on it. It just doesn't work. Yet here's SDSS J102915, glowing quietly as if it never got the memo. So how did this star cheat the system? One radical theory suggests it formed in a pocket of the early universe so untouched by supernova that it remained chemically primordial. A bubble where the first stars could still ignite long after metals had polluted the rest of the cosmos. Picture a forgotten corner of a library where the air never changed, preserving a book no one else could read. Another idea posits that the star's birth cloud was struck by a shock wave, perhaps from a nearby galaxy collision, compressing it violently enough to bypass the need for cooling. It's like jump-starting a car in sub-zero temperatures. Under extreme conditions, even the usual rules can bend. What's even more astonishing is that the impossible star didn't just form, it survived. The early universe was a brutal place, with lethal ultraviolet radiation and cataclysmic explosions ripping apart fledgling stars. For this one to endure for over 13 billion years suggests it was either incredibly lucky or forged in an environment so rare we've barely begun to map its contours. Some astronomers speculate it might be a surviving member of population Roman 3, the hypothetical first generation of stars made purely from Big Bang ingredients. If true, it's the last of its kind, a living fossil from an era when the cosmos was still writing its first recipes. Yet every answer raises new questions. If this star is truly primordial, why does it have any metals at all, even trace amounts? Could those atoms have been stolen from a passing interstellar cloud or a long-dead companion star? And why, after decades of searching, have we found so few stars like it? The universe, it seems, played a cruel trick, giving us a glimpse of its earliest days, then hiding the rest of the evidence. The impossible star isn't just a cosmic oddity, it's a key to unlocking the universe's first chapters. Its existence hints at pathways to star formation we've never imagined, and its survival suggests the early cosmos might have been far more diverse than our simulations predict. As telescopes like the James Webb probe deeper into the cosmic dawn, we might finally find others like it, scattered like diamonds in the dark. Until then, this solitary enigma stands as a reminder. Sometimes, the most profound discoveries aren't just about what the universe shows us, but what it stubbornly refuses to explain. Right now, as you watch this, an invisible hurricane is raging through our galaxy, one made not of wind or water, but of the universe's most enigmatic substance, dark matter. Discovered in 2017, this cosmic tempest, dubbed the S1 stream, is a river of ancient stars, and more importantly, their unseen dark matter counterparts, barreling through the Milky Way at 500 kilometers per second. Unlike earthly storms, you won't see it coming, you won't feel its passage, but its gravitational fingerprints are etched into the motion of stars, bending their paths like trees swaying in a phantom gale. And hidden within this silent maelstrom might be the keys to unlocking dark matter's true nature. The S1 stream isn't just another celestial curiosity. It's the shredded remains of a dwarf galaxy devoured by the Milky Way billions of years ago. As our galaxy's gravity tore this smaller neighbor apart, its stars stretched into a long, thin river stretching across the sky. But here's where the plot thickens. The stars we see are just the visible tip of the iceberg. The real mass comes from the dark matter halo that once surrounded the dwarf galaxy, now funneled into this dense, fast-moving current. For the first time, we've caught a dark matter structure in the wild, one we can map by its gravitational tug on everything it passes. It's like tracking a shark's movement by the ripples it leaves behind, even when the water itself is invisible. What makes this dark matter hurricane so revolutionary is its potential to test theories that have languished for decades. Most dark matter searches focus on static setups, waiting for particles to drift through underground detectors, but S1's high-speed stream offers a dynamic laboratory. If dark matter interacts with itself, even weakly, the chaotic environment of the stream with particles crammed closer together than usual might amplify those signals. Imagine shaking a box of sand. Normally, the grains don't stick, but if even a tiny static charge exists, patterns emerge. Experiments like LUX Zeppelin and Xeno and NT are now fine-tuned to hunt for these subtle interactions during Earth's passage through the densest part of the stream, a window that opens every 45 million years. Yet the storm also raises thorny questions. Why haven't we detected dark matter already if it's flooding through our solar system? One possibility is that it's clumpier than models predict, with pockets of higher density that our detectors have simply missed. Another wild theory suggests dark matter might be colder and slower moving in the stream, requiring entirely new detection methods. There's even a fringe idea that S1 could contain primordial black holes, hypothetical relics from the Big Bang hiding within the current. Every hypothesis carries high stakes. If any prove true, they could rewrite the rules of particle physics. The beauty of this mystery lies in its duality. On one hand, the dark matter hurricane is a tangible thread to pull, a rare opportunity to study this elusive substance in motion rather than as a static halo. On the other, it underscores how little we truly grasp. Even as the storm rages around us, its particles pass effortlessly through our bodies, our planet, even our detectors, leaving barely a trace. It's a humbling reminder that the universe's most dominant ingredient remains just beyond our grasp, its secrets carried on an invisible wind. And as we brace for the next surge of data, one thing's certain: whether S1 brings answers or deeper questions, it's proof that the cosmos still has storms we're only beginning to sense. Somewhere in the depths of intergalactic space, nature is playing a game of cosmic darts, and Earth is the target. These aren't ordinary projectiles, but particles packing so much energy they make the Large Hadron Collider look like a toy. We're talking about ultra-high-energy cosmic rays, atomic fragments screaming through the void with the force of a major league fastball concentrated into a single proton. The mystery: no known object in the universe should be able to launch them. The numbers alone defy belief. When scientists first detected these particles, mostly protons, but occasionally heavier atomic nuclei, their energy levels topped 100 exa-electron volts. That's a 1 followed by 20 zeros, or roughly the kinetic energy of a tennis ball, served at 100 miles per hour but compressed into a subatomic speck. To reach such ludicrous speeds, these particles would need accelerators millions of times more powerful than supermassive black holes. And yet, when astronomers trace their paths backward through the galaxy's magnetic fields, the trails vanish into empty space, pointing at no obvious source. It's as if the universe has invisible cannons scattered across the void, firing at random with no shooter in sight. One leading suspect is active galactic nuclei, supermassive black holes devouring matter so violently they create jets of plasma stretching millions of light years. These cosmic blowtorches might theoretically boost particles to extreme energies, but there's a catch. Even the most energetic AGN jets fall short by orders of magnitude. Another candidate is gamma-ray bursts, the universe's most powerful explosions. Yet these fleeting events are too rare and distant to explain the steady rain of ultra-high-energy particles hitting our atmosphere. Then there's the wild card: cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If these filaments vibrate or snap, they could release bursts of energy capable of launching particles across the cosmos like a slingshot. The plot thickens when you consider how these rays even reach us. Space isn't empty, it's filled with the cosmic microwave background, radiation left over from the early universe. For ultra-high-energy protons, this faint glow should act like molasses, slowing them down over long distances through a process called the Greisen-Zatzeping-Kuzmin cutoff. The fact that we detect them at all implies they're coming from relatively nearby, within a few 100 million light years. But again, searches of that volume reveal no plausible sources matching the required energy output. It's like finding footprints in the snow leading to a locked door. The evidence points somewhere, but the room beyond is empty. What makes this enigma so transformative isn't just the particles themselves, it's what they reveal about the limits of our cosmic maps. Every ultra-high-energy cosmic ray is a messenger from forces we've yet to imagine, carrying clues about physics operating at scales beyond our current accelerators. Some theories suggest they might be signatures of exotic dark matter decay or collisions between primordial black holes. Others propose their evidence of extra dimensions where gravity leaks into our universe in unpredictable bursts. The most tantalizing possibility that we're seeing the fingerprints of an entirely new class of astrophysical objects, ones too dim, too fleeting, or too alien for our telescopes to spot. Experiments like the Pierre Auger Observatory in Argentina are racing to catch more of these particles, using arrays of detectors spread across thousands of square kilometers to trace their paths with pinpoint accuracy. Meanwhile, neutrino telescopes scan the depths of ice and water for related particles that might share clues about their origins. With every new detection, the puzzle grows richer, teasing us with glimpses of a universe far more violent and unpredictable than our textbooks describe. So the next time you feel a raindrop, consider this. Trillions of neutrinos from these cosmic accelerators are passing through your body right now, utterly harmless yet carrying secrets from the darkest corners of existence. And somewhere out there, in the void between galaxies, nature's ultimate particle guns are reloading silent, invisible, and waiting for us to unravel their mysteries. Imagine a ring system so vast it makes Saturn's iconic bands look like a child's hula hoop. That's J1407b, an exoplanet so bizarre it rewrites the rules of what we thought possible for planetary adornment. Located about 400 light-years away in the constellation Centaurus, this distant world sports rings 200 times wider than Saturn's, stretching over 180 million kilometers, a distance so immense it could easily swallow the gap between Earth and the Sun. If you replaced Saturn with J1407b in our solar system, its rings would dominate the sky, appearing larger than a full moon from Earth's surface. But here's the real puzzle. According to everything we know about planetary formation, this gargantuan ring system shouldn't exist. The discovery unfolded like a cosmic detective story. Astronomers first noticed J1407b not by observing the planet directly, but by its shadows. As it passed in front of its host star, the light dimmed in an erratic pattern. Not the clean, symmetrical dip of a typical planetary transit, but a jagged series of eclipses lasting weeks. The culprit, a sprawling, uneven ring system with gaps and divisions hinting at unseen moons sculpting the debris like celestial sheepdogs herding their flock. But the sheer scale of these rings defies all expectations. For comparison, Saturn's rings could fit between Earth and the Moon with room to spare. J1407b's rings could hold over 1 billion Earths. So how does a planet grow such an outrageous accessory? One theory points to a cataclysmic collision, a Mars-sized object smashing into a young gas giant, vaporizing into a temporary disk of debris that later coalesced into rings. Another idea suggests J1407b might be a super Saturn, a failed star called a brown dwarf caught in the awkward phase between planet and star, its immense gravity hoarding material that would otherwise form moons. But the most tantalizing possibility involves youth. J1407b's system is estimated to be a mere 16 million years old, a toddler by cosmic standards. At this early stage, planetary rings haven't had time to dissipate or clump into moons, offering us a rare snapshot of a solar system's chaotic infancy. What makes this exoranged giant truly revolutionary isn't just its size. It's what it reveals about the diversity of planetary architectures. Before J1407b, astronomers assumed ring systems followed predictable templates based on our local examples. Now, we're forced to confront a universe where planets might sport rings wider than some star systems, where moons could be as common as grains in these cosmic sandbanks, and where the line between planet and protostellar disk blurs. Future telescopes like the James Webb Space Telescope could analyze the ring's composition, searching for water ice, silicates, or even organic molecules, clues to whether such systems might birth habitable moons. Yet the enigma lingers. Why haven't we found more J1407bs? Is this ringed Leviathan a cosmic fluke, or are we just beginning to scratch the surface of exoplanetary oddities? Every new observation peels back another layer, revealing a cosmos far stranger than we dreamed, where even something as familiar as planetary rings can stretch the limits of imagination. And as we keep searching the skies, one thing's certain: the universe still holds wonders that make Saturn's jewels look like costume jewelry. At the edge of our galaxy, where the Milky Way's spiral arms fade into the void, an invisible wall stands guard, one that even the most energetic particles in the universe can't penetrate. This is the Galactic Barrier, a mysterious region where cosmic rays, those high-speed atomic fragments racing through space, slam into an unseen force field and bounce back like moths against a window. Discovered by spacecraft like Voyager and the Hubble Space Telescope, this cosmic roadblock defies every expectation. If the Milky Way were a castle, this barrier would be its moat, but no one knows who or what dug it. Cosmic rays aren't just random space debris. They're the universe's bullet trains, protons and atomic nuclei accelerated to nearly light speed by supernova explosions and black hole jets. They should be able to travel unimpeded across galactic distances, which makes their abrupt stop at the Milky Way's fringe so baffling. Measurements show a sharp drop-off in cosmic ray intensity beyond a certain boundary, as if an invisible shield stretches around the galaxy, filtering out these high-energy particles. The strangest part: this barrier isn't made of matter, at least not any we recognize. There's no dense wall of gas or dust, no magnetic field strong enough to explain the effect. It's as if the galaxy itself has a built-in force field, one that operates by rules we haven't yet deciphered. One leading theory points to the Milky Way's halo of dark matter, the invisible substance that makes up 27% of the universe. Some models suggest dark matter particles could interact with cosmic rays in unexpected ways, perhaps annihilating them or deflecting them through some exotic physics. Another idea involves the galactic magnetic field, which might be woven into a complex web at the outskirts, creating a maze that traps or ejects incoming particles. Then there's the wild card. Could this barrier be evidence of something beyond our galaxy? A pressure wave from intergalactic space, or even the gravitational imprint of a long-ago collision with another galaxy? The implications ripple far beyond cosmic ray physics. If the galactic barrier is real and not some observational fluke, it could reshape our understanding of how galaxies interact with their surroundings. Normally, galaxies are thought to breathe, exchanging matter and energy with the intergalactic medium like lungs inflating and deflating. But a barrier like this suggests a one-way valve, a structure that keeps certain elements out while letting others pass. That could explain why the Milky Way's chemistry differs from the raw material floating between galaxies, a fingerprint of cosmic isolation. Yet the mystery deepens when we consider scale. The barrier isn't uniform, it's patchy, thicker in some regions than others, like a fence with missing boards. Some cosmic rays slip through, while others are turned away, hinting at a dynamic, ever-shifting boundary rather than a static wall. Future missions like NASA's Interstellar Mapping and Acceleration Probe aim to map these edges in detail, searching for clues in the trajectories of particles that manage to breach the barrier. What's truly humbling is how this enigma exposes the limits of our cosmic maps. We've sent probes like Voyager beyond the solar system, built telescopes that peer back to the Big Bang, and yet our own galaxy still guards secrets just beyond reach. The Galactic Barrier isn't just a scientific puzzle, it's a reminder that even in our celestial backyard, the universe still holds mysteries written in particles and shadows, waiting for us to decode their meaning. And until we do, this invisible wall will stand as both a challenge and an invitation, daring us to look closer at the edges of everything we think we know. The Big Bang wasn't just an explosion, it was the ultimate cosmic alchemist, forging the universe's first elements in a seething cauldron of energy. Hydrogen, helium, and a pinch of lithium were cooked up in those fiery first minutes, their ratios calculated with precision by physicists. Yet when astronomers tally up the lithium in today's universe, they're staring at a glaring discrepancy. At least half of it, and possibly as much as 2/3, has vanished without a trace. This isn't just a rounding error, it's a cosmic crime scene, and the prime suspects range from rogue stars to undiscovered physics lurking in the early universe's shadows. The case begins with nucleosynthesis, the process that fused atomic nuclei in the newborn cosmos. Based on the temperature and density of those first moments, scientists can predict exactly how much lithium should exist today. But when they point telescopes at ancient stars, celestial time capsules preserving the early universe's chemistry, the numbers don't add up. These primordial stars show only a fraction of the expected lithium, as if some invisible thief has been systematically stealing it for billions of years. Even stranger, the deficit isn't uniform. Younger stars often have more lithium than their older counterparts, flipping the logic of cosmic evolution on its head. It's like finding a library where the oldest books are missing pages, while newer editions are miraculously complete. One leading theory blames stellar assassins, specifically red giants. As these aging stars swell, their convective currents could drag lithium deep into their cores, where searing temperatures destroy it. Imagine a cosmic recycling plant where elements aren't just repurposed, but outright annihilated. The problem, even if every star in the universe conspired to burn lithium, the math still falls short. There simply aren't enough stellar furnaces to account for the missing stockpile. That's where the plot thickens. Some cosmologists propose that lithium might have been gobbled up by hypothetical particles called actions, ghostly remnants of the early universe that could interact with normal matter in ways we've yet to detect. Others wonder if primordial black holes, tiny and abundant, might have absorbed lithium-rich gas before stars could form. Then there's the nuclear physics wildcard. What if our models of the Big Bang's nuclear reactions are incomplete? Subtle errors in how we calculate the rates of proton collisions or the stability of beryllium isotopes could throw off the entire lithium ledger. The most tantalizing clue might lie in the cosmic microwave background's fine print. Faint distortions in this afterglow could reveal if lithium was unevenly distributed from the start, clumping in ways that left vast regions devoid of the element. Future telescopes, like the Simon's Observatory, will scour this radiation for answers. Until then, the missing lithium remains a cosmic cold case, one that proves even our most precise predictions can't account for the universe's endless capacity to surprise. From the eerie silence of the Fermi Paradox to the ghostly pull of dark flow, these 34 mysteries remind us that the universe is far stranger than we've dared to imagine. They're not just gaps in our knowledge, they're cracks in reality's facade, hinting at forces, dimensions, and civilizations we've yet to comprehend. Every time we think we've mapped the cosmos, another enigma emerges, laughing in the face of our models. Take Tabby's star flickering like a faulty streetlight, or the Great Attractor dragging galaxies toward some unseen finish line. These aren't just curiosities, they're cosmic breadcrumbs leading us deeper into the unknown. What makes these puzzles so thrilling isn't just their strangeness, it's what they reveal about our place in the grand scheme. For all our telescopes and equations, we're still like ancient sailors charting the ocean's edge, terrified the next wave might send us tumbling into the abyss. The difference, our maps now span billions of light years, yet the terra incognita grows vaster with every discovery. The Galactic Barrier, the missing Lithium, the impossible star, each one whispers the same humbling truth. The universe is playing a game, and we're only just learning the rules. Perhaps the greatest lesson lies not in the answers, but in the questions themselves. The Fermi Paradox forces us to confront the fragility of intelligence. The wow signal teases the possibility we're not alone. Dark flow and the axis of evil suggest our universe might be one of many, a single thread in an infinite tapestry. Even the Pioneer Anomaly, with its tiny, stubborn deviation, reminds us that gravity, the force we thought we understood, still holds secrets. These mysteries aren't roadblocks, they're invitations, daring us to think bigger, dig deeper, and question everything. So where do we go from here? The next breakthrough might come from a teenager analyzing telescope data in their bedroom, or a machine learning algorithm spotting patterns no human could see. It might hide in the flicker of a distant quasar or the spin of a particle in an underground lab. One thing's certain, the universe isn't done surprising us. And as long as there are stars in the sky, there will be mysteries waiting to unravel. Which of these enigmas keeps you up at night? The phantom galaxies built of dark matter, the cosmic rays with no source, or something we haven't even discovered yet? Drop your thoughts below, and if you've enjoyed this journey through the universe's greatest puzzles, hit subscribe. Because the cosmos is full of stories, and we're just getting started. Think you need a PhD or a billion-dollar telescope to uncover the universe's secrets? Think again. Some of the most groundbreaking discoveries in astronomy began with ordinary people, teachers, students, even retirees poring over data from their living rooms. Take the case of Dutch schoolteacher Hanny van Arkel, who spotted a strange, glowing green blob in a galaxy zoo image. That blob, now known as Hanny's voorwerp, turned out to be a never-before-seen cosmic phenomenon, a quasar's ghostly echo, illuminating a distant gas cloud like a celestial flashlight. And she found it while sipping coffee at her kitchen table. This is the power of citizen science projects that invite anyone with curiosity and an internet connection to sift through real astronomical data. Platforms like Zooniverse host dozens of these initiatives, from classifying galaxies for the Hubble Space Telescope to hunting for undiscovered planets in NASA test data. Every click contributes to research, whether you're tracking solar storms that could threaten Earth's power grids or scanning the surfaces of Mars and the Moon for unexplored terrain. The beauty of these projects lies in their simplicity. You don't need to understand Fourier transforms or spectral analysis, just a keen eye and a willingness to learn. Algorithms might process data faster, but humans excel at spotting the unexpected, the oddities that machines dismiss as noise. Consider the story of Planet Hunters, where volunteers helped identify KBC 8462852 Tabby star and its bizarre dimming patterns. Professional astronomers had overlooked it, assuming the data was flawed, but amateur sleuths noticed the anomalies, sparking a debate that's still ongoing. Then there's backyard worlds, where participants scour infrared maps for brown dwarfs and rogue planets. So far, they've bagged over 100 previously unknown objects, including some of the coldest star-like bodies ever found. These aren't just footnotes in science. They're proof that discovery isn't confined to labs or observatories. The tools are more accessible than ever. Want to search for fast radio bursts? The SETI Institute's Cosmic Project lets you comb through radio telescope data in real time, curious about asteroid composition. NASA Target Asteroids program trains you to analyze spectral data. There's even a project decoding the chatter of sperm whales, because who knows, maybe the key to understanding cosmic signals lies in Earth's own oceans. The point is, you don't have to wait for a press conference to engage with cutting-edge science. You can be part of the process, turning raw data into breakthroughs one click at a time. What's truly revolutionary is how these projects democratize knowledge. A high school student in Mumbai can flag a supernova candidate. A retired engineer in Oslo might trace the spiral arms of a never-studied galaxy. Every contribution, no matter how small, adds to a collective understanding far greater than any single researcher could achieve. And with AI now assisting these efforts, prioritizing the most promising anomalies for human review, the pace of discovery is accelerating. We're living in an era where the next great cosmic revelation could come from your laptop during your lunch break. So why not give it a shot? The universe isn't just for astrophysicists. It's for anyone who's ever looked up at the night sky and wondered, whether you spend 5 minutes or 5 hours, you're not just observing history, you're helping to write it. Who knows, the next Hannes Voorwerp might be waiting in an unclassified dataset, and the person who finds it could be you. After all, the greatest mysteries aren't meant to be solved by a select few. They're out there, whispering to anyone willing to listen.